So absorption of the light, of course the artificial light, monochromatic light, are controlled by Beer-Lambert's law. They are empirical laws. And what are these? That is, if I say incident light as the I0 and the transmitted light as the I, it depends on, one said the concentration, C, the other said the length of the passage, the path. So, and also the concentration is molar concentration, we call it E, or in short, I0 by I is equal to molar concentration is concentration and length of the path. It is E. But this was absolutely okay under certain what's called spatial conditions, fairly dilute, not very dilute, and results were very good. But later on, they found there was variation in the Beer-Lambert law. There was variation. Variation was that it was observed that if the concentration goes very high, the refractive index changes, because this Beer-Lambert law obeys only when the refractive index of the medium, the solution, is constant. When the concentration goes very high, the law, the Beer-Lambert law, does not hold good. The second, if you make it very, very dilute, sometimes equilibrium shifts backwards. That is, it depends on the refractive index, it depends on the dilution, it depends on instrument also. There are instruments and stray lights come with different frequencies and you get a very, very haphazard broadbands. Normally we don't get single line broadbands because these are disturbing factors, like every bond has what's called rotation, stretching, and all other frequencies associated with, along with the bonding energies. So what happens with the concentration? It was studied that molecules get associated. They become very much associated, mutual attraction. Or with the solvent, they form strong hydrogen bonding. With the result, they change the refractive index of the medium. The second is that if we make it very, very dilute, equilibrium changes. Say, for example, the chromate ion. It is in equilibrium with, which is in equilibrium with, so these are the equilibrium reactions of chromate, which is a color. And at the end, we get an H2. Everything in equilibrium and it should be in the forward direction. If we make it dilute, we take it, the solvent as the water, the concentration of water increases, the equilibrium shifts to the left and we get erroneous results. This is due to the chemical. Similarly, hydrogen bondage and other mutual attraction, all that. What is this refractive index? There were two scientists, Corter and Sealer. They devised that refractive index plays a role. And if we can modify the Beer-Lambert's law, that is the absorbed, that we saw the absorbance, and it is but true, n is the refractive index, n square plus 2 whole square, well, n is the refractive index. This is valued, but it is advisable for the practical work. It should not be very dilute. It should not, because very dilute equilibrium shifts, or it should not be very concentration. Not only that, the solvent plays a role. If the solvent is not homogeneous, you get erroneous results. So before you observed in the cell, which is a 1 centimeter long cell, you see that it is first taken in a standard measuring cylinder, small or a flask, shake it thoroughly so that it is uniform, then put in the cell. It should be uniform, otherwise error will come. These are the deviations from the Beer-Lambert's law.